The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. This is Elisa Baum. I'm GridGain Systems Senior Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. First, can you please raise your hand located in the GoToWebinar control panel to let me know if you can hear me? And I'm going to go take a look at you guys. Do I see hands? Can you hear me? I see hands. You guys are awesome. Thank you. Next, during this webinar, you will be on mute, but should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible, and in addition, a recording of this webinar and slides will be made available to everyone within 48 hours. I'd like to introduce today's speaker. His name is Lucas Beeler, and he's GridGain Systems Senior Technical Consultant. We're very fortunate to have him here today to do the presentation of designing multi-cluster in-memory computing applications. So with that said, I will go ahead and turn the floor over to Lucas. Go ahead, Lucas.
Oh, thank you so much, Elisa, for the introduction here. Just had a slight problem with PowerPoint. Happy to get that restarted. As Elisa said, I am a senior consultant with GridGain. I have a little bit more to say about that in my introductory slide. Most of what I do in my role as a senior consultant is I'm a professional services architect. So it's a post-sales role where I help our customers design and build complex GridGain-based applications. I actually worked at Gigaspaces, another in-memory computing platform vendor, in exactly the same role prior to joining GridGain a few years ago. And so this presentation is actually the result of my sort of hard-won experience designing and building systems for my largest clients. As you guys have probably heard from the introduction, this was originally presented at the In-Memory Computing Summit in London back in June, and it was part of the architecture track at that conference. But I'd also like to say it could just as easily have been part of the war stories track, because I am going to talk about places where I've seen classical data grid design sort of break down and how I was able to overcome them. So I think for those of you who are developers and architects, it'll be hopefully a very interesting presentation, as well as for those of you who are business decision makers contemplating in-memory data grid technology. One kind of caveat here, and it's actually listed in my last bullet point, and that is that the approach that I'm going to present may seem antithetical to received wisdom about correct or best practices in IMDG application design. In the in-memory data grid or IMDG community, we have this culture that heavily emphasizes shared nothing designs, which is to say all of the nodes in your cluster run exactly the same logic, and there are no separate kinds of nodes for separate tasks, and insofar as is possible, you want to be able to complete all of the business processes on your data, want to say on a particular piece of your data within the memory image of a single node, so that there's no network movement or no shared state across the network for nodes to perform business operations. And that's the notion of sort of shared nothing, right? They don't have to share data to complete your business workflow. I am actually going to smash that and say that there are times when this conventional wisdom about shared nothing breaks down. So just be ready for that. The approach that I'm going to present is based on building multi-cluster applications. So kind of throwing the notion of shared nothing out the window, and realizing that there are times when you might want to build a single application out of multiple clusters that each have their own responsibilities. Before we get on to defining a few terms here, I just wanted to say that I work for GridGain, but I don't just want this to be a marketing presentation solely for GridGain. This is a general talk about IMDG architecture, so I will reference some documentation from our competitors, Hazelcast and Gigaspaces, because they offer, in some ways, similar functionality. Obviously, I think GridGain is the best IMDG platform, or I wouldn't be working there. But the point is that the ideas in this talk will help you to think about in-memory computing design, regardless of platform. And I hope it gives you an idea of just kind of how far we've come in thinking about architecture for these systems at GridGain, which is one place where I think we're ahead of a lot of our competitors. Just to define very briefly here, a multi-cluster application is, as I said, a single application whose functionality is implemented over multiple in-memory data grid clusters, each with its own responsibility. You might have one cluster for data ingestion or another cluster for analytics. For our purposes, a cluster is a distributed in-memory data grid, and IMDG like Gigaspaces, GridGain, Hazelcast, etc., that supports co-located processing. And I can't emphasize the co-located processing aspect here enough, because it's probably the most powerful feature of modern data grids, but it's also what gets you into the most trouble. Because if you think about it, all of the machines in your data grid, in your cluster of 8 or 10 machines, they have CPUs, right? So in addition to storing data in memory, they also form a massively parallel compute cluster where services and compute tasks and continuous queries can operate on the data stored in that cluster. So each node will not just hold data, but it will be actually running code on top of that data. So that's why I say that co-located processing is very important here. And if you've entered into the world of co-located processing, which is to say you're no longer just using your grid as sort of a dumb cache to stick objects in, but have started really building business logic on top of it, it's co-located processing that can get you into difficult scenarios, even though it's the most powerful feature of these products. In fact, I'd say precisely because it's so powerful, it's why you can shoot yourself in the foot. An application in our case here is a deployable set of code artifacts that deliver a coherent, unified collection of business functions. These code artifacts are usually deployed to your cluster nodes. Your cluster nodes may have multiple artifacts on them. They're all unified in that they represent a single application. Oftentimes, all of your code artifacts are deployed in a single jar that's placed on the disks of your cluster nodes. In a multi-cluster design, we're going to be talking about not deploying a single code artifact, but having multiple code artifacts that sort of have different personalities and are deployed to cluster nodes of different kinds. And we do this for separation of concerns, orthogonal evolution, and for scalability. I'll define what I mean by those a little later, though they may already be pretty clear to many of you. The agenda of this talk is to first give a conceptual overview of modern in-memory data grid functionalities. I'm sure that not all of you are using IMDGs yet. A lot of people attend webinars when they're considering technologies, or they're in sort of a pre-purchase or POC phase. So for those of you who are there, I'm going to kind of give an overview of what modern in-memory data grids like GridGain offer you. I'm then going to give an example of a traditional single cluster application built on top of GridGain that does a lot of amazing stuff but has certain limitations. And then I'm going to talk about how we can overcome those limitations by transitioning that sample application from a single cluster design to a multi-cluster design. I'm then going to talk about some case study implementations. These are systems that I've actually built for my customers at GridGain that represent multi-cluster use cases that are in production. And finally, we'll leave some time at the end for a Q&A, because I'm sure you guys will have plenty of questions. moving on to our first topic, which is sort of functionality provided by modern in-memory data grids. Obviously, everybody here probably knows the value of the first point, right, which is in-memory caching of data, right, in its native object form. I want to say a little bit about the native object form thing for a moment, though. Oftentimes when people talk about in-memory data grids, they think that so much of the performance win comes from keeping stuff in memory. And that's completely true, because memory is about 1,000 times faster to do a main memory lookup than even to do a random access from a modern SSD. However, there's another huge advantage. And I'll step back and say there are kind of two kinds of in-memory products out there. There are in-memory databases like Times10 and SAP HANA. Then there are in-memory data grids like GridGain, Hazelcast, etc. In-memory data grids store objects in memory in their native object form. So if you're coming from a Java background, this means you're actually storing objects as POJOs, right? Now they may be marshaled or serialized, but they're basically binary objects. So you don't have to go through any object relational mapping in order to insert, data into your grid. It's not as if you have an object and it has to be mapped into a row with a series of columns in it. No, you just do a simple put operation and the entire object is cached in memory in the grid. And this is an incredibly performant idea, and it's one of the ways that these systems realize their power and speed, because ORM is pretty expensive. Like if you've ever worked with Hibernate and all of the stuff that it does as an object relational mapping framework, it uses the Java reflection mechanism to try to auto map from fields into columns. The Java reflection mechanism is pretty slow. ORM is expensive. In fact, there was an article several years back in one of the more prestigious industry publications like InfoWorld or eWeek that stated that something like 20% of enterprise CPU cycles are spent doing ORM. So you avoid that in an in-memory data grid, which is, I think, one of the reasons why these solutions are much more attractive than databases, whether they're in memory or on disk. So that's storing things as objects, which is the basic purpose of an IMDG. But these solutions that are state-of-the-art have all been extended to be able to do analytics, for instance, right? And common analytics operations are, things like type classification, right? So what kind of a thing is this, right? You have a customer object that's stored in your grid. You want to classify that customer as someone who is likely to spend big or not spend a lot, or someone who's likely to buy shoes or not buy shoes, so that you could, in your e-commerce site's marketing, target them with specific targeted advertising. There's also, in the analytics realm, people use IMDGs to do domain-specific performance analysis. So in investment banking, for instance, this is usually, how well did this trading strategy perform versus the S&P 500. In retail, it might be something like, how well did our last marketing campaign work? But the basic idea is that because these systems keep objects in their native form and they allow you to run code co-located on top of those objects, it's very easy to do analysis like this in a way that was not possible with traditional systems without batch processes. So we do stream ingestion and ETL operations. Most of the modern in-memory data grid products can act as stream sinks for things like Kafka or ActiveMQ. And when objects arrive, they can be ETL'd or enriched or transformed into a more sophisticated state. They provide event processing functionality, which is sort of like triggers in a database, but it's a mode of reactive programming where you can say, okay, a new customer purchase transaction object just arrived in my data grid. Now I need to react to its appearance and say notify a downstream system to settle the payment. Some customers are using IMDGs to provide a local mirror of SaaS data on-prem that mirrors what they have up in the cloud in a SaaS service, or to push data to a SaaS service when it changes locally. So that would be an example of a kind of a reactive operation is, so yes, I got this customer transaction object that came in, I detected it, now I will react to it by pushing it up to a SaaS service. And because you have both direct object storage and SQL or SQL-like languages that allow you to query objects directly, IMDGs are great to integrate many data sources into sort of a unified queryable store, so that that data can come from, as I said, a SaaS service, it can come from an on-prem data warehouse, but you can stick it all into your IMDG, and the IMDG can become a unified integrating platform that holds data in a unified format in their native types as business objects. Now, all of this is actually, you know, pretty awesome, but you can see that IMDGs actually offer a lot of functionality that you can deploy on a single node, and that's actually where things can become problematic. You deploy so much functionality that it can overload your individual nodes, and you have to start thinking about separating functionality out. So in terms of how do IMDGs accomplish such a range of tasks, as I said, I wanted to make this presentation not just GridGain specific, so I borrowed this from our competitor Hazelcast, and this is a slide from their training site. But the one thing that I will point out here is that, yes, there's caching in the upper left-hand corner, but in the bottom, you'll also see this notion of messaging, right? And so messaging, what's implicit in there is that there's a notion of a message, there's a notion of when a message arrives, and that when a message arrives, you can react to it and transform it. So this is what I'm talking about the richness of these solutions. They're not just dumb object stores. Moving on to some content from Gigaspaces. Here, I took this from the Gigaspaces documentation site. Here we see 3 Gigaspaces server nodes. That's where you see processing units on the top row, right? And in Gigaspaces, what you would think of as a table in a database or a cache in other IMDGs, if you think about it, a database table is a logical place to store data of a particular type. In the Gigaspaces world, that's a space. And so the spaces are represented here by little clouds. And so what you're seeing here in this top row is that there is a space that is sharded among all of these 3 servers. So each server has a fraction of the data in the space, but on each server, there's also a service implementation. So you can run code on top of that data within the same memory image where that data lives. And those services can be invoked remotely from the client that you see on the bottom by way of a proxy. So I'm getting at how powerful these solutions are. When you start thinking about streaming, services, co-located compute, you have a lot of functionality. GridGain, I would say, perhaps delivers the most sophisticated functionality of them all, which is one of the reasons why I am very happy to work there. As you can see from this little puzzle diagram that we use, we've got a data grid, which caches objects, but we've also got compute grid. You can run massively parallel compute tasks on top of your objects. We've got service grid, so similar to that Gigaspaces example I showed where you can deploy services into your grid. We just added machine learning functionality, machine learning primitives in your grid to classify objects in your grid and do that kind of type classification that I talked about earlier. And then down here at the bottom was a quote from Forrester that I think is very telling, and it's, you know, IMDGs in general suffer from a caching stereotype, and that's sort of coherence, for instance, which is kind of a dumb object store. But the interesting thing here is that, you know, Forrester says GridGain smashes that stereotype by offering a general purpose compute grid. If you need an in-memory data grid that caches things and a supercomputer all in one, then take a look at GridGain. To a lesser extent, this applies to Hazelcast and Gigaspaces as well. All of these systems provide very rich functionality that allow you to run code and services co-located with data. Moving on, let's actually think about an application. So we've talked about all these wonderful things that IMDGs can do, but let's talk briefly about an application that uses all of this functionality. And we'll talk about you know, how the application works, how it's built, how it's pretty awesome on its own, but also how there are certain moments when things can break down under heavy load, and how we might change the system so that that doesn't happen. And that's the transition from a single cluster design to a multi-cluster design. So our application, let's imagine that we're a regional bank. We have 12 branch offices and just over 100,000 customers. We do all the usual things that banks do. So we take deposits. They could be checks, cash, electronic, direct deposit, etc. We allow withdrawals. We issue credit cards. You might have a Bank of America Visa card, or a Wells Fargo Visa card, or a Chase Visa card. That's, your credit is underwritten by that bank, but the card transactions are actually processed through a processing network like Visa or MasterCard. We make loans, and we manage relationships with our customers because we'd like our customers to engage with more of our products. This is classic CRM or CEM, the latter being customer engagement management as opposed to customer relationship management. The basic idea is, for example, if we know that you just got an auto loan from us and you have good credit, well, we might want to send you marketing about taking out a mortgage, right? So we want to be able to know what our customers are doing to engage with them further. And also, let's assume that we're a US-based company, so we have to comply with a fairly sophisticated regulatory framework that includes things like the Dodd-Frank Act and Sarbanes-Oxley. If we take a look at the kind of basic overview of our application, it looks more or less like this. There are several ingestion actors. So these are ways where we can get data into our cluster. There are also several query actors, which are things that take data out of our cluster, and there are also several push receive actors, which are things that our cluster sends data to under well-defined conditions. You'll see at the heart of this is GridGain, a modern in-memory data grid made up of 4 cluster nodes. Let's assume they're pretty beefy. They're, you know, got 512 gigabytes of RAM each in these cluster nodes. Our ingestion pipelines, let's take a look at those first, because that's a logical place to start in terms of the data flow. They are Visa, obviously, so every time someone swipes a credit or debit card that we issue, a transaction has to be received, right? There's also Fedwire and the automated clearinghouse. So ACH is used to process almost all checks in the United States. And believe it or not, I still have to write like 5 checks a month for rent and medical appointments and things like that, right? So we're not entirely beyond the realm of checks. So there's still quite a lot of those coming in. And Fedwire is a Federal Reserve system that's used for interbank transfers, both if you were a bank and you want to borrow money at the overnight rate from the Federal Reserve, or also to send transactions between banks. So I get paid by direct deposit, and GridGain sends a Fedwire transaction from GridGain's bank to my bank, you know, every 2 weeks. So these are common bank ingestion use cases. In terms of our query actors, we've got branch terminals. If you go into a bank and you want to withdraw cash, you know, you need to look up your balance. A branch terminal, I'm also including ATMs in there where you need to query balances and things like that. And then I'm also assuming that there's a query actor for settlement processing, which is something that happens in the financial sector generally at midnight Eastern time, right? Where we might queue up transactions during the day and then settle them or clear them for the next business day. We have a cloud CRM service, so this could be something like Zora, or Salesforce, and that's where we push our marketing information to, right? So if we notice a customer doing something that might be important from a marketing standpoint, for example, if we see an auto loan payment come in and we might decide, well, let's queue this up and send it to our cloud CRM service so this customer gets included in a future campaign to receive mortgage offers. And we also have an audit database, which is where we send receipts for regulatory compliance, things like Sarbanes-Oxley and Dodd-Frank. So this is sort of the basic overview of our system. And, you know, I want to just talk for a second about how awesome this is, because if we step back and look at this diagram, there are no other systems here other than the GridGain cluster. We're not seeing like an Informatica tier where Fedwire and ACH transactions that come in as XML or plain text are ETL'd into a POJO and then put into the cluster. No, all of the ETL, all of the stream receiving, that's being done in the cluster itself. Likewise, we're not seeing any kind of REST gateway like an IBM REST or web service appliance, right? We don't need anything like that to push our data to our cloud CRM service, because that can all be done as a service within the cluster node. I mean, a service inside of a cluster node can run arbitrary Java code, including the full Apache Commons HTTP client library to make as many REST pushes as we'd like, and REST posts to our cloud CRM system. And our branch terminal and settlement processing query actors can actually use standard SQL syntax. And frankly, they don't know that they're not hitting a database, that they're actually hitting a live object store that's processing stuff. Even though those may be legacy systems that are designed to communicate via SQL. So yeah, this is pretty awesome. I mean, yeah, we can process transactions, but also, you know, when a customer uses his or her ATM debit card to get cash at a foreign cash point, we detect that through something that GridGain, for example, calls a continuous query. It's called different names in different systems. And while continuous query may give you the idea that it's a polling system, it's actually event-based. But if you see an object, a customer transaction object for a foreign transaction come in, you can check if that customer, I'm assuming that the cache that stores all of our customer data is also in the same cluster. We can check to see if that customer has our SkyPoints Airline Rewards MasterCard, and if they don't, we will push out a notification to our cloud CRM system to enable that customer to be included in a future marketing campaign for the SkyPoints Airline Rewards MasterCard. And the system provides us with really rich primitives for building this functionality. I already sort of talked about continuous query, but we also have Stream Receiver and Stream Transformer, which are the key ETL tools in GridGain. These are Java classes, which is why I've put them in a typewriter font. You can check them out in the GridGain Java doc. And we can implement our entire rules engine using the compute service and event processing APIs in the data grid itself. So it's pretty amazing that we can do all of this. And what does this really mean to you as someone thinking about buying one of these solutions? Well, first of all, it's fewer licenses, right? You don't have to buy Informatica to do ETL. But the other thing it is it also means that your developers are dealing with less cognitive weight. they're not working with multiple tools. They're working with one tool that has similar design patterns shared throughout its APIs, right? So think about how much you pay your developers if you're a decision maker, right? They're not cheap. They make, you know, six-figure salaries. Every time you have to train them on a new tool, that's burning time that could be used on development projects to help your business, right? But because of the functionality offered by this IMDG, right, we're able to do things like, if I can mark this up very quickly with a blue pen here, you know, there may be a raw XML document from Fedwire come in. GridGain's stream receivers are smart enough to be able to receive this on exactly the cluster node where it will ultimately be resident, because, pardon me, sorry, I had a little error with my pen there. Yeah, so if we take our pen, yeah, well, here's our X. I am so sorry. It seems like there was a problem using our pen in PowerPoint. Well, let me skip the pen then, and instead we'll drop back to the old PowerPoint laser pointer. Yeah, so we can imagine that you know, our XML comes in here, Fedwire, it's sent directly to the cluster node where it will ultimately live. It comes in a stream, it hits one of these stream receivers, and then the stream transformer will convert it, will parse the XML or the plain text into a POJO. It will then be a fully high-graded Java object cached in the grid, and we can run services on top of it. Once it becomes a high-graded object and is stuck in the grid, we can detect it via a continuous query, see that it matches criteria to include the associated customer in a marketing campaign, and push that right out to the cloud CRM. But notice that the data never has to leave this cluster node once it comes in. It's all co-located in this one cluster node. All of these services are in one node, right? The Fedwire stream receiver, the cloud CRM pusher. That's phenomenal because there's no network traffic. And this is what we call a classic shared nothing design. So the nodes do not have to share any state in order to accomplish your business workflow, because all of it is implemented within, your entire business workflow can be implemented within a single node. And while your data is sharded between nodes, so let's say you have 10 pieces of data, this first node might have data pieces 1, 2, and 3. The second node might have data pieces 7, 8, and 9. This cluster node will be working on 1, 2, and 3 in parallel, while this cluster node is working on 7, 8, and 9. But the point is that the data doesn't move once it's in the cluster node. The entire business workflow could be completed on it. That's a classic shared nothing design that in-memory data grids are really known for. And that's co-located processing. So you're co-locating all the processing with the data. And as I said, we implemented this by following best practices, right? It shared nothing for maximum co-location. All our cluster nodes are identical in configuration. They can complete our entire business workflow in a single memory image. You know, we can do the ETL in the same node where the POJO will ultimately reside. You see this as this kind of fourth major point down here. You know, we can stream the Fedwire transaction receipts directly to the same node where the final customer transaction POJO that corresponds to the receipt will be stored. We can push REST JSON messages directly from processes in the nodes or services in the nodes to our cloud CRM system. And if we want to increase total system capacity, all we have to do is add another node. I mean, it's pretty amazing. But so what's on every node to do all of this? Well, we've got to have our actual customer transaction POJO instances. So every node has to store a shard or portion or partition of the data. We've got our FedWire stream receiver, our ACH stream receiver, our cache store adapter for the audit database that's going to push, it's going to do ORM and push things into a permanently auditable, say, SQL data warehouse. We've got our cloud CRM pusher service, the query services for our batch terminals and settlement processing. These are pretty fat nodes, right? They've got data instances and they've got a lot of processes on them. And this is the natural inclination that people have to do things once they realize how much you can do with modern IMDGs. Which is amazing, but what happens at midnight Eastern time? At midnight Eastern time, that is generally when FedWire and ACH notifications are broadcast between banks. So at that point, these cluster nodes, because they do everything, they have the stream receivers on them, but they also store data, and they also allow batch terminal queries. They can become so saturated performing FedWire and ACH ETL operations, parsing that XML or text, because they're just being slammed, that all of the other pathways, the queries for settlement processing, pushing to the cloud CRM, etc., all of those other pathways experience resource starvation. There simply aren't enough threads to do the work. Most of these systems are based on a notion of a single sort of thread pool for these activities. Now, you might say, well, one way we could overcome this would be to do some very sophisticated thread management. I've seen customers try to do that. I would heavily caution against it, because if there's one thing I can tell you, and you probably know this if you're a developer, right, is that starting to mess around with your own thread management inside of a container that already manages threads can lead to really non-deterministic and almost impossible to debug kind of nonlinear starvation behavior. So let's forget that idea and go to the next logical decision, which is, all right, let's add extra capacity, right? All of these systems are designed for scale out, so we'll add another cluster node. And we add another cluster node, and yes, it has a FedWire stream receiver and an ACH stream receiver, which are frankly what we really want to do. We want to process more of these messages. But unfortunately, because we followed a traditional shared nothing architecture, what we also get is holding customer transaction POJOs, having a cloud CRM pusher service, having a branch terminal query service, and all of the other stuff that we talked about. They're all co-located, so they're all deployed on this node when this node comes up. And one of the things that has to happen is, because this node will actually hold data, all of these systems elastically rebalance. So when you add a new node, the cluster will attempt to provide a uniform distribution. If you have 4 nodes, every node will hold about 1/4 of your data. And if you have 5 nodes, every node will hold about 1/5 of your data. So you bring this extra thing up, and suddenly you start getting network data movement, which is the biggest thing you wanted to avoid by doing shared nothing in the first place. So I posit a better way, which is, let's leave shared nothing behind, and let's instead have multiple clusters. These can be physical or logical clusters. In GridGain, you can implement both. In other solutions, you may be constrained to only doing what we call physical subclusters. The individual clusters within a multi-cluster application, as I said, are called subclusters. Within a subcluster, you have shared nothing. There is uniform provisioning and horizontal scaling. They still apply within a subcluster. It's just now that we have multiple subclusters. We'll see a diagram of how this works in just a second, and I'll talk about all of the wonderful advantages of it. But first of all, just to be straight with you guys, I want to go through kind of what we give up going from a shared nothing architecture to a multi-cluster design. One of the things is that DevOps isn't simple anymore, right? We don't just have one cluster node image that we can deploy and spin up. We now have several, because we're going to have clusters of different kinds with different kinds of nodes in them. we can no longer scale the entire system by adding another node. Instead, we have to scale along different scaling axes. And I'll explain that a little more in just a second. But basically, each subcluster represents a different scaling axis. So you scale subclusters independently of each other. The other thing is that we can't complete our entire business process without sharing data between nodes. That is to say, without data moving over the network between nodes. So we've broken shared nothing across the entire cluster, though we still have shared nothing within an individual subcluster or tier. We're going to talk about what we gain over the next few slides. So imagine we refactor our bank application to look like this, from having one cluster to instead having three clusters, three subclusters. We have an ingestion subcluster, a data subcluster, and a cloud pusher subcluster. So the ingestion subcluster is stateless. It doesn't store any data. All it does, these are basically compute nodes or service nodes that know how to ingest FedWire or ACH, XML, or plain text. They know how to parse it into a POJO, and then they know how to put that POJO in one simple operation very quickly in its fully hydrated POJO form from the ACH receiver into the data node. Doing a put between nodes that share the same Marshall data format is a virtually instantaneous operation, other than the network transfer time. And indeed, the network transfer time of pushing the POJO over once it's been built is totally dwarfed by the amount of compute time that you have in order to do the XML parsing, right? So our data nodes are free from ever having to do any XML parsing or plain text parsing, and hence they can respond to queries much more rapidly, even under heavy ingestion loads. Likewise, our data nodes will send a request POJO to the cloud pusher that will then handle communication with the external cloud CRM service. So the data nodes don't in and of themselves have to hold an HTTP client. We've basically made our data nodes more as just storage and query nodes, as opposed to these rich, highly functional nodes that are running a lot of services. So the way that you do this in GridGain, it's pretty simple. If you want to have nodes of different types, you just set different user attributes in the node's configuration XML. And for example, here I'm setting a user attribute for a node to be a Fed ACH receiver. And through some magic in GridGain, we can set up a subcluster of all of the nodes that are tagged with the Fed ACH receiver role, which would be these nodes here, right, that receive FedWire and ACH messages. So the immediate advantages are sort of what I talked about. All the ETL operations are separated from the nodes that store data. Queries don't slow down when ingestion volume is high. Plus, we have the advantage that we can bring down our ingestion subcluster over here and upgrade the ingestion logic without having to bring down our data nodes, right? And every time you bring down a node that has data, data has to be rebalanced, right? The other thing is that when you bring down a data node, while all of these systems provide fault tolerance through backups of data that are kept on other nodes, until that backup replication SLA is met, and it won't be when a node immediately goes down, you are in a situation where the cluster is in an intermediate topology state. And that's when clusters are most vulnerable and bad things can happen to good clusters. So this is orthogonal evolution. So, you know, orthogonal, mathematical term meaning two axes that meet at a right angle, like the X and Y axis. You can evolve along one axis, your FedWire receivers, and on another axis, your data nodes, without having them affect each other at all, which is not true in the shared nothing fat node case. You can also scale orthogonally, right? I mean, here we see it's midnight. We want to add another FedWire ACH receiver. That's great. Add another one of those. There's no data rebalancing because our data subcluster isn't affected. Likewise, we want to add more data capacity. Don't really care about having more ingestion speed. add another data node. This is the notion of orthogonal scalability. These two things can scale along entirely separate axes, right? And their scaling is independent of each other. So you don't have to just have this, take a hammer to, it's not like having a single node that's a hammer and it's a tool for everything. Nodes become more fine-grained tools. So having said all of that, I think we get the idea of how these multi-cluster designs work. So I'd like to take the last 5 minutes that we have before we go into questions to present some case studies of actual customer systems that I have built with my clients that are based on this concept. And one of the kind of things that I'd like to talk about first is one of the design themes surrounding a lot of the use cases where multi-cluster designs are very useful. And one of those design themes is command query responsibility segregation. This has been a pretty hot topic in enterprise architecture right now, and has been for a few years. I took this blog post from Martin Fowler. Martin Fowler is one of my favorite authors on enterprise architecture. I mean, heck, a lot of you guys on this call are probably reading his blog too. He's definitely a thought leader. He wrote a great description of command query responsibility segregation. The basic idea is that you can use an entirely different model to ingest data, that is to say the command phase, versus to get data out, which is the query phase. And you don't have to be a rocket scientist to see that this maps very well into a multi-cluster design where you have one cluster for the command stage and another cluster for the query stage. Indeed, that is the theme of my first case study, where our customer is a large wealth management firm, have about $1 trillion of assets under management. They may well manage your pension fund. They had a requirement that queries to other enterprise systems be extremely fast, so on the order of microseconds, to feed the trading desk and whatnot. However, information arrives in this system in a primitive format, so it has to be enriched before it can even be queried. So the architecture here was kind of, we set it up so there was an ingestion cluster and a data cluster. An ActiveMQ event stream pushed in a lot of unenriched trading events. We then enriched those through a GridGain service, which you see, oh, sorry, I lost PowerPoint again, excuse me. We then enriched those through a GridGain service and a GridGain continuous query that you can see. We had intermediate caches for objects in various stages of enrichment. And this actually required us calling out to an enrichment database. But by the time the object was fully enriched, it was just a marshaled POJO, actually in the GridGain marshal format, so it was very easy to push it right over into the data cluster from which queries were made. So these external actors, the other enterprise systems, could query through a web service facade on the order of microseconds, given that they had an InfiniBand interconnect in their data center. Even though there was a heck of a lot of stuff going on over here, including a slow database query. So we retained the ability to access data quickly, even though data ingestion was slow. And that couldn't have happened without the CQRS design and multiple clusters. The other case study here comes from one of the largest fitness center operators in the US. They're one of our retail clients. They've got about 300 gym clubs and 4 million members. They made a decision to move most of their customer engagement management and subscription management into a cloud-based customer engagement management SaaS provider. And that was so that they didn't have to do this themselves. They could focus on you know, upgrading their clubs, figuring out how to offer better Pilates classes, as opposed to handling credit card billing every month. The problem that they ran into was that they had concerns about the 24/7 availability of data stored in the SaaS provider. I mean, heck, even Netflix and Google's Gmail site have gone down in high-profile outages that we all know about because they've been in the media, right? So what if you can't get to the SaaS provider? Also, the SaaS provider has its own data model, right? Its own sort of JSON schema. And that data model is not compatible with the customer's internal legacy systems. Also, you can only put certain kinds of things in the SaaS system. So a lot of business data still has to be kept on-prem, right? The solution that they went to was to set up 2 GridGain clusters, one of which they used as a data store subcluster that integrated both SaaS and on-prem objects. So these would be domain objects that were important to them, subscriber, payment, etc. Some of them were legacy objects that could not be stored in the SaaS system, and others were SaaS objects that were mirrored locally. And we had this fetcher subcluster set up that every 15 minutes would pull a change set from the SaaS provider and then feed it into the data store subcluster. So at least within a 15-minute window, you would have on-prem a total mirror image of what was in the SaaS cloud-hosted service, along with all of your on-prem data as well. And you could access this through the JDBC and ODBC clients provided by GridGain, in which case it would look like a traditional database, or you could access it through the GridGain native client. So that pretty much wraps up this presentation. A few final remarks on the case study themes. You know, in both of our cases, the reason why multi-cluster worked is because things that we had to do dwarfed the amount of time that would be required to do network data movement between nodes in a cluster. In one case, we had a WAN link to a SaaS provider. In the other case, we had to do these compute-intensive ETL operations. Those are kind of good indicators for when things might work for you with this sort of design. And finally, as a closing remark, just my experiences with these multi-cluster designs have caused me to sort of envision a capability maturity model for in-memory computing that starts with caching objects, which is basically just, you know, it's a dumb data grid, let's put POJOs in it, to then co-located computation, which is deploying services, deploying continuous queries, that sort of thing, where we integrate everything, all of our business processes into a shared nothing architecture, to finally realizing the limitations of that and moving to multi-cluster applications, which is what I see my largest and most sophisticated customers doing. So that concludes my portion of this presentation. Thank you all for attending. I will take questions now.
Hi, it's Elisa. Okay, thank you so much. I have some questions for you. Are you ready?
Yes.
Okay, great. So the first question that we have here is, you mentioned that you could use both logical and physical subclusters to implement multi-cluster designs in GridGain. Can you talk more about that and about the advantages and disadvantages of each?
Yeah, I will. So in GridGain allows functionality that other IMDGs don't necessarily, which is called cluster groups. And it's described in our documentation on the Apache Ignite documentation site. As you probably know, Apache Ignite is the open source flavor of GridGain. Check it out. The idea is that you can, within a single cluster, assign different roles to different nodes. So I call these logical subclusters because technically it's still a single cluster, but it hosts different kinds of nodes. So that's a logical subcluster design that uses cluster groups in GridGain. The advantage to that is that it's all still one cluster, so you don't have to deal with inter-cluster proxies. The disadvantage is that deploying services can be a little tricky. there's some delicacies there where you can run into problems. A physical subcluster design is where you actually have multiple clusters that are completely separate, and the nodes in one cluster hold a proxy or client to the other cluster. I hope that made sense.
Okay, great. Next question. Can you please contrast the differences between GridGain and Apache Ignite?
Yeah, sure. Apache Ignite is a fully capable open source in-memory data grid solution. It is a great way to build POCs and whatnot. What it lacks, I would say, are some of the stuff that you really need if you're going to go into production. So one of the things lacking in Apache Ignite is very rich management and monitoring. That's obviously problematic because in an actual deployment scenario, you probably want to get fine-grained metrics about what your cache latencies and throughputs are. You want to see what the load on your nodes is. We have a lot of cool monitoring tools that give you great graphical dashboards, or you can connect GridGain enterprise nodes to something like Dynatrace or AppDynamics for monitoring. So monitoring is one, it's pretty enterprise critical. Another one is data center replication, which is, if you have multiple data centers and you want to replicate data between them for disaster recovery, that's an enterprise-only feature. And then the final one is, while both Apache Ignite and GridGain allow durable memory, that is to say the ability to persist data that is held in memory on disk for durability. So if you have a power failure, you can restart your nodes and not have to reload data because memory is volatile. What open source Apache Ignite lacks is the ability to take a point-in-time snapshot. So GridGain will allow you to take a point-in-time snapshot of all the data in your grid at 7 p.m., for instance, while the cluster is running. And if you experience a data corruption event, which is often the result of human error, right? I mean, somebody enters something wrong and you have to roll your cluster state back to a known good point in time, a known good snapshot. GridGain will allow you to do that, but open source Apache Ignite won't. So most of the differences concern production readiness, I would say. Hope that answered your question.
And there's also support too. I think that you should mention some of the support features that come with GridGain.
Oh, well, yeah. Sorry for skipping over that. I was speaking in terms of technical features as a technologist. Obviously, Apache Ignite, the only support you get is the community. GridGain, you can get 24/7 support with an hour SLA if you want. Elisa, did that kind of express, I think, what you were looking for there?
That was great. Yeah. So does anyone else have any questions for Lucas? We're coming to the top of the hour. I think people have a couple of seconds to think about it. I do want to thank everyone for attending today's webinar. And Lucas, thank you for a great job. And we hope to see you again on a future webinar. Everybody here. Oh, wait, guess what? We just got another question. Okay, so what is a good place to find more information? Where can you go to find out more information about GridGain and Apache Ignite?
So the best place that I would recommend going is the overview documentation site, which is apacheignite.readme.io, right? It's got a lot of great material about getting started, as well as links to reference pages like the Java doc pages and whatnot. If you actually get into sort of doing a POC with open source Ignite, which is very common. Another thing that I would say is there's the IMC Planet website. There are the In-Memory Computing Summit conferences that we have, which is where this presentation came from. Attending those can be great. Also, on the GridGain website, we do a lot of cool blogs that are applicable to both GridGain and Ignite, right? So we explain how durable memory works. So I would say those are all great places to get going, but apacheignite.readme.io is really probably the best place to get started with Ignite and GridGain. And one kind of addendum to that is that One of the cool things about Ignite and GridGain is that unlike, say, Gigaspaces or Hazelcast, which are mostly closed products, Apache Ignite is a top-level Apache product. So if you do have a question about it, you can usually Google it, and you'll get like a Stack Overflow answer about it, because the community, the open source community, is large and robust. Along with that community come the Apache Ignite developer and user mailing lists that you can subscribe to. And if you just Google Apache Ignite user mailing list, you can subscribe to that. There's a lot of great discussions that go on there about, you know, hey, I tried to use this, it didn't work. And the community is usually, you know, usually you'll get 3 email responses saying, this is how I got it to work in, I don't know, 5 hours or something. Yeah. Hope that answers your question.
Okay, great. And I also want to point you to gridgain.com. We have 2 really good white papers. I'll include them in a follow-up email to this. One is called Introducing Apache Ignite, and the other one is called Introducing GridGain. And papers are pretty clear about the differences in each and when you're ready to move from an Apache Ignite more into a production environment, like Lucas mentioned. So I'll include links to that, as well as the links to the Apache Ignite forum that people are asking for. Okay, fantastic. Well, I think that brings us a little bit over the top of the hour. Again, Lucas, thank you for a great presentation. Audience, we hope to see you on a future presentation. And with that said, I will go ahead and close out the webinar. Thank you again, Lucas, and everybody.
Thank you, Elisa. It's been my pleasure.